Hello everyone. In the upcoming videos, we are going to discuss about MOSFET. These are the concepts I would like to cover in the upcoming videos. The basic MOSFET structure, its operation, along with the DC circuits, and how a MOSFET is going to be functioning like an amplifier. Then the small signal analysis. Right. To discuss about the MOSFET amplifiers, first of all we need to aware of what is basically a field effect transistor. Before going to the field effect transistor, let me cover one important concept called what are the advantages of FET over BJT. Why we are preferring FET over the traditional bipolar junction transistor. Let us see what are the advantages we have. We know that in case of a BJT, which is called as a bipolar junction transistor, the current conduction is due to both majority as well as the minority charge carriers. But in case of field effect transistor, we have only the majority charge carriers. We don't have any minority charge carriers. That's why the field effect transistor will be called as unipolar device. Only one charge carrier which is responsible for producing the current. That's why it is called as a unipolar device. We know BJT is a current controlled device. The output current is controlled with the help of the input current. But in case of a field effect transistor, we call it as a voltage controlled device. Result, the output current is controlled by the input voltage. Yes, this is one major advantage. FET has a very high input resistance when compared over the BJT. Another advantage of FET is it provides thermal stability. Though we have a temperature variations, but still FET is capable of producing the constant output voltage and the currents. BJT is going to be producing the noise whenever it is trying to operate. The reason is that the current conduction is due to both majority as well as the minority. Due to the movement of the minority charge carriers, it produces a small amount of a noise. Whereas the FET, it doesn't produce noise because the current is due to only the majority charge carriers. That's why we can call FET is very high immune to noise. Right. Now, let's get back to the classification of field effect transistors. We have two types of a field effect transistors. One is a junction field effect transistor. Another one is called metal oxide semiconductor field effect transistors, which can also be named as insulated gate field effect transistor. This is the overall classification. Again, the JFET is divided into N-channel JFET, P-channel JFET. MOSFETs is also divided into enhancement and depletion, where you are trying to create a channel. Here, the available channel is going to be removed, called as a depletion MOSFET. Again, we have in enhancement, we have N-channel enhancement MOSFET, P-channel enhancement MOSFET, N-channel depletion MOSFET, P-channel depletion MOSFET. Whenever it is an N-channel, the current conduction is due to electrons. Whenever we say P-channel, the current conduction is due to holes. It's very simple. Right. Let us get back to the N-channel JFET. The first one. This is the basic structure of junction field effect transistor, which is an N-channel. We have taken an N-type semiconductor on both sides of the N-type semiconductor. We are doping with the P-type. Both the P-types are connected together. Take a terminal, call it as a gate. One side of the N-side bar take one terminal called as a source. Another end take one more terminal called as a drain. and we have a metallic contacts which is going to be making a contact with the semiconductor. We call it as ohmic contacts also. Means this basically the FET is consisting of the three terminals: source, drain and gate. Charge carriers starts at source, moves towards the drain. Meaning is the movement of the charge carriers always takes place from source to drain. This is what is the movement of charge carriers, irrespective of the type of the FET. The movement of the charge carriers, or you can call the channel, can be controlled with the help of a terminal called as a gate. That is the purpose of each and every terminal. Gate is used for controlling the channel width. This is the channel. The channel width is controlled by the gate, and charge carriers always moves from source to the drain. This is the basic symbol for N-channel JFET. Now let us come to the biasing and the working of the N-channel JFET. The working of the JFET purely depends upon the biasing voltages what we are applying to the JFET. Let us see the biasings. In order to control the channel width, say here this is a P-type and this is an N-type. It's a PN junction diode. It appears like a PN junction diode, means it's a PN combination. It also like a PN. That's why both the P-types are connected together. We are calling it as a gate terminal. Means whatever the voltage I am applying to the gate, same voltage it has been applied on either sides of the P-type semiconductor. Now I want to vary the channel width. That is possible only whenever I keep the gate under the reverse bias. Reason is, here it is one PN junction. This is the junction we have. The depletion width can be varied by varying only the reverse bias voltage. If I increase the reverse bias voltage over the gate, the depletion width between or across the P-type and N-type semiconductor is going to increase. Similarly, how much a depletion width variation taking place here, the same amount of a depletion width variation is also going to take place, because the same voltage we are applying to this P-type as well as to this P-type semiconductor. Right. Now, that is why gate is always connected under reverse bias. See, the gate is of the P-type, but here it is connected to the negative terminal. Now let us come back to the source and the drain. Always charge carriers starts at source and they are going to be moving towards the drain. If it is an N channel, the charge carriers has to move from the source to the drain. Electrons are always attracted towards the positively charged, because they are all negatively charged particles attracted towards the positive terminal of the battery. If they want to attract towards the drain, certainly the drain has to be connected to the positive. Then only the negatively charged particles called electrons will attract towards the drain, which is a positive terminal. Defaultly, the other terminal we need to connect to the negative. This is a very simple biasing phenomenon or the technique used in case of the FET. Gate is always under reverse bias, whereas the gate voltage we need to apply based on the what type of a charge carriers. Depends upon what type of a channel it is in the JFET. Now, we know that the depletion region or the depletion width can be varied by varying the VGS. I can have the maximum channel width when VGS is equal to 0 volts. Here VGS is kept as a 0 volts. Then I have the maximum channel width here. If I have the maximum channel width, then if I try to increase the value of VDS, and more number of electrons will be attracted from source to drain. If more number of electrons are attracted towards the drain, certainly the drain current is going to increase. Means that the output drain current can be controlled with the help of both VGS as well as the VDS. VGS helps to control the channel width. VDS helps to control the movement of the charge carriers from source to the drain. Now, this is another phenomenon where here in the first case where we have the gate voltage is equal to 0. Here we have slightly increased the gate voltage, which is equal to 1 volt. Because of applying a small gate voltage, here we have a depletion region. Let us discuss why the depletion region is not uniform. And the depletion width will be more towards the drain and the depletion width will be less towards the source. The reason is that, see here, this is the P type and an N type. For the P you have connected already a negative. For the N type, see here, this end of the semiconductor N type is connected to the positive. Means the drain is more reverse biased when compared to the source. That is the reason why the channel width or the depletion width towards the drain is more when compared with the depletion width towards the source. That is the only reason why the shape of the channel will be like this. Right. If we still increase the value of VGS, automatically this depletion width is going to be increasing. Whenever the depletion width increases, this channel width is going to reduce. Let us see in the next slide. See this case. Previously, the VGS value has been applied is 1 volt. Now here the VGS value applied is a 4 volts. As a result, the channel width has reduced. If the channel width has reduced, the number of charge carriers that can be able to cross the channel is reduced. Whenever the number of charge carriers moving from the source to the drain is reduced, certainly the drain current also reduces. What we try to say here is, as we are increasing the value of VGS, depletion width is increasing, the effective channel width decreases. If the effective channel width decreasing, the number of charge carriers moving from source to drain decreases. If the number of charge carriers moving from source to drain decreases, the drain current also decreases. But the drain current also depends upon VDS. If I don't apply any VDS value, if I keep VDS equal to 0, no charge carriers called electrons will be attracted from source to the drain, though I have a VGS. If I don't apply VDS, there is no movement of electrons from source to drain. In order to have a movement of the charge carriers from source to drain, we need to increase this value of VDS. That is the reason why both drain current is going to be depending upon VGS value as well as VDS value. This is the characteristic. We are already mentioning. See, VDS, we have ID, which is an output characteristics, or VA characteristics simply we call, and we have a maximum drain current. We have a maximum drain current at VGS is equal to 0. As VGS value we are trying to increase from 0, minus 1, minus 2, minus 3, minus 4, the channel width decreases. Channel width is going to decrease, thereby the drain current decreases. That's what is indicated in the VI characteristics. In this we have the 3 regions. One is ohmic, another one is a saturation, another one is a breakdown region. Let us understand that what is exactly meant by this ohmic region, saturation and breakdown regions. Ohmic region, you try to increase the value of VDS, ID also you trying to increase. That is what is basically ohmic region. In case of a saturation, where the drain current is remaining as a constant, still you try to increase the value of VDS, ID remains as a constant. That is a saturation region. Then, whenever this drain current is a constant, you try to still increase the value of VDS. Definitely there is a possibility for a breakdown of the junction called a PN junction. Certainly the current is going to increase. Then there is every possibility for the damage of the MOSFET. JFET. That is what. For every value of VGS, we have an effect called as a breakdown due to higher voltages of VDS. These are the three regions of operation in case of JFET.